This is a combined unit that looks at tests and measures for interval ratio level scale data and difference between means tests. Tests of significance and measures of association for interval ratio level data operate similarly to tests for categorical data. Different tests are used more commonly by different disciplines, but they operate on similar principles. If you master any of these tests, you can master others. I'm going to begin by discussing situations in which you have categorical independent and interval ratio level dependent variables. These are usually difference between means tests. The test of significance you usually use in these cases would be either a t-test or ANOVA. T-test tests the difference between two means. ANOVA tests the difference between more than two means. The measure of association used in either of these cases would be eta. Next, we're going to discuss the correlation coefficient, Pearson's R, and R squared, when you have interval ratio level variables. In this case, this will give you both your test of significance and your measure of association in one. T-tests are appropriate for when you have interval ratio level dependent variables combined with a categorical independent variable. T-tests test the difference between two means. If you have more than two categories in the independent variable, you would simply run multiple tests testing the difference between each mean. You could have a direction in your test. You could hypothesize that one is going to be greater than or less than, or you could have no direction, specifying simply that there's a relationship. Of course, a direction will be revealed by the results of your test. Hopefully, an example will help clarify. This is a real example that I'm using from an ongoing research project that I'm working on with several students. In this case, we're looking at the relationship between how a country scores on the Human Development Index and different facets of that index, in this example, the Gender Equity Index, and participation or success in the Winter Olympics, the 2014 Games held in SOCHI. So here's an example for you. Hypothesis 1. I'm going to predict that there's a relationship between the score of a country on the Human Development Index and participation in the 2014 Olympics. The null is that there's no relationship between participation in the 2014 Winter Olympics and one's score on the Human Development Index. In the second case, I'm predicting that the score on the Human Development Gender Equity Index is predicted by participation in the 2014 Winter Olympics. The null is again that there's no relationship between the score on the Human Development Gender Equity Index and participation in the 2014 Winter Olympic Games. Remember, the 2014 Olympic Games is actually a two-category variable. Yes, that country participated. No, that country did not participate. The score on the Human Development Index is an interval ratio level piece of data. It's a numeric score. The lower the score, the higher the country is ranked. So keep that in mind. A lower score is better in this case. First, I take a look at the summary statistics. On the Human Development Index, there's 81 countries that did participate in the Winter Olympics and also had a score on the HDI. Sometimes there's a little disconsonance there as to whether a country is scored and whether or not it exists in HDI standards. 105 countries did not participate in the Winter Olympics. For countries that had scores on the gender index, and this is because some countries are not scored on this index, 71 participated, 76 did not. The average score for countries that participated on the HDI index is 57.96, almost 58. The average score for countries that did not participate is 121. On the gender index, the average score for participating countries is 46, while the average score for non-participating countries is 101. I think there's going to be a relationship here. When I look at the independent samples t-test table, what I look at is the sig two-tailed column. You can see here that in both cases, both of my tests received scores of p-values of 0.000. This is less than 0.05. There is a percentage out there somewhere. It's just more than 3 decimal places out. What this means is that p is less than 0.05. Both my tests were statistically significant. I can reject the null in both cases. In fact, I can label both of my tests highly statistically significant. It's less than 0.01. Again, keep in mind, this doesn't tell me the strength of the relationship. I need a measure of association to do that. Eta is the appropriate measure of association. When we look at eta, we have to consider which is the independent and which is the dependent variable. Does participation predict your score, or does your score predict your participation? I'd have to think your score predicts your participation. In that case, there's a very strong correlation between participation in the Winter Olympics and one's nation's score on the HDI. This isn't surprising. The Winter Olympics require a great deal of capital to participate. Effectively, I picked an example that I knew would have a strong relationship. In both cases, I have highly statistically significant results and strong values. House country scores on the HDI and the HDI Gender Equity Index is a strong predictor of participation in the Winter Olympics. This tells me something about globalization, the effects of colonialism, and inequality today. ANOVA, analysis of variance, compares differences in means among subgroups in a sample. It's going to determine if the differences in mean values between 3 or more groups are by chance or if they are indeed statistically significant. In order to use ANOVA, we have to meet certain assumptions. That it's a normal distribution, that it's a random sample, and that each group's variance is equal. So again, our 3 assumptions for ANOVA are that the sample is random, that the sample is normally distributed, and that the distribution within the populations are equal. We can test for this third. We used Levene's homogeneity of variance test prior to conducting ANOVA to make sure that we can use ANOVA. If we don't pass this test, we're going to have to use a different method. So let's take a look at an example. I hypothesize that there's a relationship between geographic location by continent and the total number of national medals won in the 2014 Olympics. The null is that there's no relationship between geographic location by continent and the total number of national medals won in the 2014 Olympics. In lab, we'll go over how to run an ANOVA and how to take a look at the descriptive statistics and run Levene's homogeneity of variance test. First, let's take a look at the descriptives. Here I have the 6 continents that include countries that could participate in the Winter Olympics. There aren't any in Antarctica. I suppose the penguins could try. As you can see here, the N represents the number of countries on each of those continents that participated in the Winter Olympics. We're also working on getting the data for the Summer Olympics for comparison. When I ran my ANOVA, I asked SPSS to give me a homogeneity of variance test. It's going to give me Levene's. In this case, what I'm looking for is in the sig column. I need there to not be a statistically significant difference between the range of values between the groups. What that means is what I'm looking for is that the sig value for Levene's is not less than 0.05. Effectively, conceptually, what I'm looking for here is that I have all these different groups. Each of those groups has its own standard deviation around the mean. What I'm looking for is how different are those standard deviations. If they're too different, I can't compare these groups. Now in this case, I can. Levene's p-value is 0.251. It is not statistically significant. I may use ANOVA. Taking a look at the sig column there, we can see we do not meet the p-value 0.05 criterion. Our significance is 0.086, not quite there. I still think there's some evidence of a relationship because we would meet the 0.1 criteria. I think that the difference in the number of nations per continent may have had an effect. I'm going to be including the summer data and weighting the data in the future to test it again. One thing I might want to do here is still take a look at the measure of association to see if I'm going to see any evidence of a relationship that might lead to me wanting to pursue these next steps. Taking a look at ETA in this case, I have to first decide which is my dependent variable, the continent on which the nation resides, or how many medals it won. I'm thinking that since the continent can't change, that's got to be the independent variable, and the number of medals won is the dependent variable. I have an ETA value of 0.547. Again, this would lead me to conclude that maybe there really is a relationship here, even though I can't reject the null right now. And I probably should start taking a look at some of the other steps I could take to investigate this further. So to sum it up, I would report this as, well, we cannot reject the null. My F value, that's the value of ANOVA, is 2.347 with a p-value of 0.086. However, I am seeing some relationship, some evidence that there is a relationship, p less than 0.1 and ETA 0.547. Pearson's R is a measure of association and test of significance for interval ratio level variables. R squared, the coefficient of determination, is R squared, and it gives you the proportion of variation in Y that is explained by X, making it very easy to interpret. I've included the formula for R here, but again, you're not going to have to calculate it. The computer's going to do that for you. What's important is you constructing a good hypothesis out of our data and then understanding the results that the computer distributes to you. We're going to focus on testing the relationship between two variables. However, be aware that multiple correlation coefficients can also be tested using linear regression. We're going to touch on this at the end of the class. We're also going to go over how you can actually include a categorical variable in a linear regression equation with the use of dummy variables. R squared, the coefficient of determination. R squared is a statistical measure of how close the data is fitted to the regression line. It is also known as the coefficient of determination or the coefficient of multiple determination in the case of multiple regression. It's a percentage or the response variable variation that is explained by a linear model. R squared is always between 0 and 100. 0 indicates that the model explains none of the variability. 100% would indicate that the model explained all of the variability. It would be a perfect prediction. In general, the higher the value of R squared, the better the model fit, though with social science data, we don't expect to have very high values for R squared. I have several examples of hypothesis tests using the bivariate correlation command. In this first case, using one of our Empire data sets, I looked at income and body mass index. Obviously, body mass index is a terrible measure. It doesn't take into account lots of other factors, but it was some interval ratio level real-world data. I would hypothesize that the higher your income, the lower your body mass index. And this test confirms it. What you're looking at here is one of the squares where household income of all respondents and BMI intersect. What you see here is in this first cell in the table, household income intersects with household income. That's got a perfect correlation. In the next cell to the right, body mass index intersects with household income. Here we see an Pearson's R value of negative 0.123. The number under that is the significance. You see it's labeled sig two-tailed. That's 0.001. In this case, my p-value is less than 0.05. I meet the test for statistical significance, but it's a fairly weak negative relationship at negative 0.123. If I square that, I multiply negative 0.123 by itself, I get an R squared value of 0.015. 1.5% of the variation in body mass income is explained by household income. It's statistically significant, it's just not having a particularly strong effect. Here's another example. I hypothesized that the ratio of female athletes that a nation sent to SOCHI would be predicted by that nation's score on the Human Development Index. Again, you want to look at a cell in which the HDI gender score on the Human Development Index intersects with the ratio of female athletes. In this case, we see a Pearson's R score of 0.393 with a significance at the level of 0.002, p equals 0.002, less than 0.01, highly statistically significant. If I square 0.393, I come up with an R squared value of 0.15. In this case, 15% of variation in what proportion of your team is female is explained by a nation score on the Human Development Index. A nice feature of the bivariate correlation is that you can have multiple tests in one table. I might want to look at correlations between several variables at the same time. In this case, I can put the Human Development Index, the Human Development Gender Equity Index, the total medals won by a nation in the Winter Olympics in SOCHI, and the total number of medals won by women from a particular nation in SOCHI, all into one table to look at the correlations. By doing this, I can see right away that there's a very strong correlation between your score on the HDI and your score on the HDI Gender Equity Index. That's not surprising at all. But I can also see that there is a statistically significant relationship between your score on the HDI and the total medals won by women, but there is not a statistically significant relationship between the HDI and the total number of medals won, though it's pretty close. Here's another example from a survey from one of the California primary elections. In this case, I created two indexes, one of economic liberalism. The higher one was, the more neoliberal or conservative one was. I also created an index for how one felt about immigrants. The higher one scored, the more restrictions one wanted on immigration. I have to admit, I was being a little bit obnoxious here, because those who are neoliberal claim they want no restrictions on free market trade. So I wanted to see what sort of restrictions they'd wanted to put on labor. Not surprisingly, there was a statistically significant, moderate to strong correlation between wanting to put restrictions on immigrations and wanting to put no restrictions on economic trade. Seems a little bit hypocritical, doesn't it? Regression analysis uses correlations to plot linear relationships. It allows for a prediction of the dependent variable from the independent variable. The logic of regression is based on the best fit regression line. It's based on that old formula from a line that you might remember from geometry, y equals mx plus b, but in statistics we rewrite it as y equals a plus bx. A is the y-intercept, or the point at which the line crosses the y-axis, and b is the slope of the line. Here's an example that shows the relationship between r and the line. In each of these cases, you see some data plotted, the best fit regression line, and the corresponding value of r. The tighter the data is clustered around the line, the better the line describes the data, the higher the value of Pearson's R. Let's take one of our examples with the regression analysis. Again, let's say the lower one score on the HDI, the more medals that country will win in the Winter Olympics in 2014. The null is, of course, again, there's no relationship between the score of a nation on the HDI and the number of medals won in SOCHI 2014. Okay, let's take a look at our results of the regression equation. In the first table, we can see here the value of r and r squared. 19% of the variation in how many medals won in the Winter Olympics is explained by a nation's score on the Human Development Index. Keep in mind, nations that did not compete were not included, of course. Looking at the second table, what we see is first the constant and then the beta. The way this works is we would predict the number of medals won by a nation in SOCHI by their score on by the constant 15.430 plus their score on the Human Development Index multiplied by negative 0.146. Here's a graphic representation of the results. It's a scatter plot with the best fit regression line added. As you can see, some of the data seems to be tightly clustered with a few outliers. So to summarize my results, I can reject the null. There's a statistically significant relationship between the score of a nation on the HDI and the number of medals won in SOCHI 2014. P equals 0.023. To predict the number of medals won by a nation, I would use the formula y equals 15.43 plus negative 0.146 times that nation's score on the HDI. To some degree, I think this is a better measure because there's a limited number of medals that can be won, but a fairly large number of athletes can attend. When I look at my results, I see it's highly statistically significant. I have an R of 0.477 and an R squared of 0.228. 22%, almost 23% of the variation in how many athletes are sent to the Winter Olympics by nation is explained by that nation's score on the Human Development Index. It's statistically significant with p equal to 0.000. If I were to construct a formula to predict how many athletes were sent to SOCHI, I would use the constant 48.679 plus that nation's score on the HDI times negative 0.356. Here's a graphic representation with a scatter plot with the best fit regression line added. So to sum up my conclusions, I can reject the null. There's a statistically significant relationship, and I can use the following formula to predict the number of metals won. In future modules, we'll look at how to do this with multiple regression equations.